By way of surveying the room, how many people here have heard in a physics context the phrase WIMP? Good, that's the correct answer. All right, so how many people, okay, a better question. How many people understand the pop culture reference in the title? 1, 2, and 1 is my student. I'm a little surprised. Okay, today's talk is less a colloquium and more a public service announcement about dark matter. Some context, this talk actually came out of discussions with Laura a year and a half ago at the Kavli Institute for Theoretical Physics, where there is a really cool conference that included astrophysicists and particle physicists. And towards the end of the conference, I think it was 2 weeks long, you were one of the organizers, right?
No, I just attended.
OK. Well, there was a fantastic conference nonetheless, largely because of Laura's participation. And towards the end, I stuck around because I like the beach and the science. They go hand in hand. And a group of astronomers came to talk to me and said, so we noticed that you people, and you people being particle physicists, you people keep talking about how astronomy is important for finding dark matter. But from this conference, half of you said we're going to discover the WIMP tomorrow, and the other half, like me, say the WIMP is dead. So what the hell? And this will be the point of this talk. So by the way, today is the 31st of October. It's a holiday. So thank you very much all for being here on a holiday. It is International Dark Matter Day. This is actually a thing. So thank you, Mike, for dressing up for Dark Matter Day. Very appropriate. Here is the outline of the talk. We will say a little bit about dark matter. You've heard this bit over and over again. We'll say something about the WIMP. And the main point here is actually we should have a working definition for the WIMP. Right? The big problem that we noticed from 2 years ago is that there is a failure of science communication, not only between particle physicists and astronomers, but even particle physicists and themselves. So from the WIMP, we'll go to the main part of the talk. This is the comic which I was referencing in the title. It's actually a decent comic. Not the best, it's decent. Which talks about the mythology of Superman. So what this talk is about is the mythology of the WIMP, the weakly interacting massive particle, as a candidate for dark matter. We will close with a lamppost, because every single particle physicist talking about dark matter talks about lamppost. Why lamppost? Because when you lose something in the dark, you search under a lamppost. All right. Any questions? Yeah, and that's where we are. Any questions at this point? One question. John, my biggest worry is that you owe me homework to give back to the first years. All right, moving on. Everything you need to know about dark matter to understand this talk is on this slide. The most important thing, dark matter exists. Let's all get on the same page. Does anybody disagree with this statement?
What do you mean by existence?
So, good. This is all, yeah, good. These are all good questions. If we're all happy with the existence of dark matter at some level, then we can proceed. There will be a group of people who, no matter what I say, will not be convinced about the existence of dark matter. And if there are any of those people in this room, well, good luck with the next hour of your life. So this is the way most dark matter talks start, right? Dark matter exists. And there are these pictures that look like every other picture in every other talk. The main point is there is proof for the existence of dark matter. All of that evidence comes from the sky. It's all astronomy and cosmology. Rotation curves, clusters of galaxies smashing into each other, the cosmic microwave background, my personal favorite. And the point is, there is really strong, fantastic evidence for the existence of a new particle that is not part of the ordinary particles that make up a chemistry. Everything that goes into chemistry is this little tiny slice. And it turns out the universe has a lot more. And of course, if you see this and someone says, I'm going to tell you about this little red slice, you're all thinking, isn't there a bigger problem? Right? What about this 70% here, this dark energy? And the difference between the red slice and the black slice is the red slice is something where I actually believe in my lifetime we might make progress in answering what this red slice is. This black slice, I have no idea what it is, and I have no reason to believe that we'll make progress in the near future. I hope we do. Good. So this is where we are. This is where we want to go. Some people might still feel like, oh, in dark matter, maybe it's modified gravity, maybe something funny happens with string theory, maybe something weird. Is it primordial black holes? Sorry, Simeon just came in. And people are like, this is all perfectly valid, right? Oh, maybe it's antimatter hiding somewhere. Right? This is the type of thing that you hear when people talk about dark matter. So here is the advanced version of the previous slide, thanks to my colleague Katie Mack. And again, there's actually lots and lots of evidence for a new particle. All of it comes from astronomy and cosmology. But not only, what's really important is it is data coming from different places and at different times. Right? This is not some weird local phenomenon. OK, so we should all be on board. Either dark matter exists or hold your peace. All right, so what is the status on the particle physics side, right? Everywhere here, like, OK, astronomy, cosmology tells us there is missing matter. Great. There's a problem. We should figure out what that is. What do the fundamental physicists say? Well, we say weird stuff like this. OK, so this slide is kind of a joke, but there are lots of younger people in the room, so maybe we should kind of break this down. In 1948, there was a presidential election between Harry Truman and Dewey. And the Chicago Tribune misread the polls, and they wrote down Dewey defeats Truman. Now, for those who know American history, things actually turn out the other way around. So the following morning, here is Harry Truman holding up the first example of presidential fake news. OK, so we all get the reference? Some of us were around to vote for this? So people like me say things like, oh, yeah, WIMPs are dead, right? This WIMPs, this weakly interacting massive particle, this nice candidate for dark matter. And then even from the same community, other people say, no, they're not even slightly dead. And so can you blame our colleagues when they say, OK, you dark matter theorists, you should get your house in order, and then you should tell us what we're looking for. So there is a puzzle. And the puzzle really is a linguistic one. So let us start with a definition. Let's all put our mathematician hats on. Let's start with definitions. A definition for the WIMP. All right. Who knows what WIMP stands for? Just as a poll. I was like, yeah, good. So people are listening. Good. Weakly interacting massive particle. And if you hear that word in vacuum, it means almost nothing. Right? Weak. Relative to what? Do you mean weak as in feeble or weak as in the W boson? Interacting. With what? Right? There's a sentence structure there. It's massive. OK, everyone in 231 knows saying something has a big mass means nothing because mass is dimensionful. It's massive with respect to what? How massive is it? And it's a particle. Good. In what sense is it a particle? Maybe the sophisticates in the room would say, oh, well, we know that everything you do is field theory. So in some sense, these quantum fields maybe behave like classical fields in some regimes. Or maybe they do weird clumpy things. Maybe they're not partically. Maybe they're weird conformal stuff. So these are all valid questions the moment I say weakly interacting massive particle. And you hear people say it over and over, weakly interacting massive particle, weakly interacting massive particle. And it just doesn't mean anything. So let me pull out of the nether regions of my life a definition. For this talk, in my life, for all of my students, weakly interacting massive particle means this. Weakly means electroweak, the weak nuclear force, the things that cause neutrons to decay into protons. Interacting. It interacts with other electroweak charged things, the Z boson, W boson, the Higgs, leptons, quarks. Maybe not all of those things, but certainly some non-zero subset of those things. OK, this is now getting pretty arbitrary, right? I am now mandating things. It's not clear why I should mandate them. Massive. What mass scale? Electroweak mass. Right? You see how this game goes. The Higgs boson is 125 GeV. That is roughly 125 times the proton mass. The heaviest particle we have in the standard model is the top quark, which is about 175 times the proton mass. I will take massive here to mean somewhere between 50 times the proton mass to 1,000 times the proton mass. Completely arbitrary. Particle. Yeah, it's a particle. In the regime of the types of experiments that we do, this thing is a particle. It's not a field. It's not some wishy-washy axion thing. It's not some clumpy thing. It's not some conformal thing. It's a particle. Good. In some sense, you should feel happy. In some deeper sense, you should feel like, well, that's a completely arbitrary thing that you've made up. Why is this a meaningful thing to define? And sure, you can define this thing and say it's dead or not dead, but why would anyone ever care about this definition versus any other definition you could pull out? All right. I will back myself up a little bit. There is a definitive history of dark matter, which is actually quite a surprisingly riveting read. And they talk about the history of the phrase WIMP. And they talk about the two colloquial uses. One is it was originally intended, the way some people use this, as any dark matter candidate that's a particle. And this is where the confusion from within the community comes from. Particle physicists will say, we're looking for WIMPs, when what they really mean is we're looking for dark matter with these properties. More recently, my definition, which may be a little bit more rigorous, is kind of what people think about. WIMPs mean interacting through the weak force, that same force that causes nuclear beta decay. There was an original WIMP that fitting this classification, which is neutrinos. Long story short, dark matter is not neutrinos. All right, so let's get to the good stuff. We have some definition for the WIMP. Maybe this is dark matter, maybe not. We want to understand the mythology for how we got here. OK, so Superman, whatever happened to the man of tomorrow? So Wikipedia calls this an imaginary story. Thank you, Wikipedia. Superman is indeed imaginary. But it's a mythology of Superman from the Silver Age. What I'm about to tell you is a mythological history of dark matter. This is neither factually true, in which case you should go here, but it's morally true. Right? In the same way that we would tell parables, we, like back in the day, would tell parables to give some moral truth, even though the literal story may not be true. What I want to tell you is an origin story for the WIMP to explain how we got to, oh, we should discover the WIMP. The WIMP is defined this way. The WIMP is dead. We should look for something else. I just want to understand how did we get to this really weird point where we have these conferences where we're talking across each other. All right. And so we should start with particle physics, and we should start in the 1990s. So imagine the 1990s, Backstreet Boy, Northridge earthquake, LA is still on fire, Bill Clinton, and the discovery of the top quark. The crowning achievement of the standard model for that decade. So particle theorists see the standard model like this. You could put on a business card. What's important is that it's a table. It's organized. Each row is a particle. So these are quarks. These are other types of quarks. These are leptons, another lepton. The spin tells you whether it's a matter particle or a force particle. These are all matter particles. These are the fundamental forces, the strong force that holds the proton together, the electroweak force, hypercharge, which is related to electromagnetism. There are numbers here related to the charges. Those of you who took 262 with me know what these boxes and box bars mean. Suffice it to say that if something has a box, it means it interacts through the strong force. If it has this funny 1, it means it does not interact. Right, you can interpret this how you will, but you can appreciate that there is structure to this. Or there's a theory behind this. You show this to one of your theory colleagues, and they know exactly what you're talking about. Even in the 1990s, we knew that everything above this line, which we discovered, was not the whole story. And you can guess what the whole story is. It had to do with the Higgs. But the reason why we knew this wasn't the whole story has nothing to do with what gives the gauge boson masses, which is what a lot of people say. It has nothing to do with why do fundamental particles have mass. It has to do with something called unitarity of WW scattering. Even in the 1990s, I could say hypothetically, if I took two force particles, the W boson, and collided them as a theorist, meaning on pencil and paper, I calculate this, and I get a scattering amplitude, right? Everyone had High-Bose class. If you calculate this, and you imagine that these W bosons hit each other with higher and higher energy, the magnitude of the scattering amplitude becomes bigger than 1. And that's bad, because in quantum mechanics, probabilities have to be conserved. So probability amplitudes should have norm less than 1. And what this was telling us was either there is something missing in the theory, something critical, or the theory does something weird and becomes strongly coupled, weird dynamics happens. But we knew that this happened at exactly the TeV scale, 1,000 times the proton mass converted into energy. We knew this theoretically. This is not, oh, I kind of feel like this is a problem. This is a mathematical fact. Either something happens and we would discover it at the Large Hadron Collider, or our foundations for all of theoretical physics has some weird loophole. That is good motivation to actually build a collider. Notice this is the 1990s. No one said anything about dark matter, which is representative of particle physics at the time. So again, this is how theorists see the Standard Model. This is how experimentalists see the Standard Model. Sorry. This is how theorists see experimentalists seeing the Standard Model. But what's remarkable is with this motivation, there's no lose. We have to discover either the Higgs boson or something like it or something exotic. You rapidly go from this to this. And then you rapidly go from this to this. And then we pat ourselves on the back, celebrations, Nobel Prizes, everything is great. Now what? OK. So let's actually rewind, because 2012 was not the death of particle physics, right? As some Mayan cosmologies predicted. Let's go back. Even in the 1990s, even recognizing we would probably discover the Higgs, even if we went back and you told the physicists in the 1990s it is a Standard Model Higgs and that's the answer, there were still big questions. One question was the biggest question, and that's the hierarchy problem. It turns out that theoretically, it really did not make sense that the Higgs boson would be 125 times the proton mass. It really didn't make sense. It had to be. The experimentalists told us, look, if you do this WW scattering, you need to have something there at around 100 to 1,000 times the proton mass. We knew that. But the theorists also knew if that answer were true, there is an immediate follow-up question, which is called the hierarchy problem. And it's such a big problem, we gave it capital letters. There are other problems in particle physics, which now in hindsight we recognize, hey, these are also big problems. But again, 1990s, Backstreet Boys, we were not caring at all about these other problems, by and large. OK, what is the hierarchy problem? Technically speaking, the hierarchy problem is the statement that the Higgs boson has a snowball's chance in hell of being 125 GeV. And I actually mean that as a very careful technical analogy. So what's this guy's name? Senator Ivanhoe? Let me not say anything because I'm being recorded. Suppose you took an ice cube and brought it to Congress, right? You take an ice cube, and you have an oven, you're baking cookies, 400 degrees Fahrenheit. You open up the oven, and you put the ice cube in there, and you close the oven, and you wait 5 minutes. You know what state the ice cube is in. That thing is melted. And you know that it's melted because it's in a thermal environment. The thermal environment is hot. It imparts energy onto the ice cube. These hot air molecules impart their energy onto the ice cube. The ice cube picks up that energy, and then it probably melts. Well, OK, the first years may not yet know this, but certainly the second years who took Kirill's qualifying exam, you know that the partition function in StatMech looks just like the partition function in quantum mechanics with up to a factor of I and maybe h bars if you care about h bars. And in the exact same way, if you replace the thermal randomness of statistical mechanics, the thermal randomness of this oven, with the quantum randomness of the quantum vacuum, then the effects of virtual particles on the Higgs boson causes the Higgs mass to get heavier. You expect the Higgs mass to be not just a little bit heavier than 125 GeV, but actually maybe 10 to the 15 times heavier. Right? So for the field theorists in the room, the Higgs mass is an unprotected, relevant operator. It has no reason at low energies to be the value that it is. Yet here we are. Okay, so 1990s, dreaming of the Higgs, listening to Backstreet Boys, and the hierarchy problem. So theorists had something to do while the LHC was being built. We had to solve the hierarchy problem. And we did. We had this magnificent, elegant mathematical theory called supersymmetry. Hurrah! And supersymmetry in a nutshell is, for every matter particle, like the electron, you have a supersymmetric partner, which is a force particle. We give them stupid names: selectron, supersymmetric electron. For every force particle, like the W boson, there is a matter particle called the WINO. So if you want to dress up for next dark matter day, that's the costume to go for. And so what? It turns out that when you think about the quantum vacuum, the contribution of virtual matter particles has a minus sign relative to the contribution of virtual force particles. So if I arrange things such that every matter particle that contributes to the Higgs mass has a partner force particle that otherwise has the exact same properties, same quantum numbers, then that minus sign exactly cancels its contribution. Hey, that's pretty neat. And in fact, it's all nice and mathematical. You just wave your hands, write down Lagrangians, and it all pops out. And it is analogous, in this oven analogy, as if I had this magical oven protected by supersymmetry, where, again, ice cube, open up the oven, 400 degrees, put the ice cube in, close it, and the ice cube does not melt because I have arranged that every time a hot particle hits this ice cube lattice from over here, there's exactly another hot particle with the same energy and opposite momentum, such that they hit the crystal lattice and they both bounce off, imparting zero energy onto the ice cube. Right? Now, we all know Avogadro's number is huge, and that's just impossibly improbable. But at least the principle is not insane. It's a magical, mathematical, supersymmetric oven. So great. I don't know, 1996, let's say, we're all done. Everything is done. We've solved the hierarchy problem. Except, things never really work out the first time. It's never really as elegant as you want it to be. This is why, as physicists, we do perturbation theory. And so a little bit of additional work was required. Because supersymmetry, by virtue of doubling the number of particles, mo particles, mo problems, right? So here are examples of new particles. These are down-type squarks. They're predicted by the symmetry that we made up. So if we solve the Higgs problem, we get these troublesome little guys. And what this diagram is proton decay. Okay, the cognoscenti in the room know it's actually anti-proton decay, but same difference. These weird particles allow certain processes that cause a proton, or anti-proton, anti-up, anti-up, anti-down, to turn into, this will probably be a pion and a positron. All of this is predicted because I just waved my hand and said, double the number of particles, and everything has the same properties other than force and matter. Well, that sucks. We need to fix that. Well, one good way to fix that is to impose an additional symmetry, a smaller, supersymmetry is this big space-time, elegant symmetry. Let me impose an additional symmetry, some parity, right? I'm just pulling it out of my pocket. There's a formal definition for this thing called R parity. I have no idea what R stands for. What it boils down to is every ordinary particle that we know exists, is even. Every new particle, every partner of an ordinary particle, is odd. And it turns out if you impose this parity, you can cross off a bunch of terms in your Lagrangian, prohibit a bunch of interactions. Namely, these interactions are prohibited, and so proton decays don't happen. The universe is stable, right? If protons decayed, none of us would be here, so that's good. There's an additional effect. If you have a population of particles that are all odd, charged under some parity, if you take the lightest such particle, because it carries some conserved charge, kinematically it must be stable. Right? There is nothing it can decay into that would carry that charge. So automatically, again, I've said nothing about dark matter. Automatically, I have a new particle that is stable. It seems to stick around. Well, that's kind of interesting. And so right around this time, particle theorists started thinking, oh yeah, our astronomy colleagues said something about some new particles that are sticking around in the middle of our galaxy. Yeah, it's probably this, right? Yes, it's probably this. Good. So what's the journey so far? Now we finally put this thing on the map. There's some missing mass. But the big problem was always, why is the Higgs boson so light? Okay. The answer was supersymmetry, some deep, elegant, beautiful, magnificent, blah, 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 symmetry principle that prevented the Higgs from getting heavy. Great. But it was problematic because it gave you new particles. New particles give you new problems, like the stability of the proton. But that's OK. This is a smaller problem, and we can put in some additional symmetry. What that symmetry does is it gives you some conserved charge. That means the lightest new particle is stable, which means, oh, that's probably a dark matter candidate. Good for me. I wasn't even trying to solve dark matter. In fact, we know a lot about this dark matter candidate. Right? We know what the mass is. It's roughly 100 GeV. Why? Because it is the partner. It's related by asymmetry to particles that are 100 GeV. It has a weak scale mass. How does it interact? Oh, it has weak scale interactions. Why? It inherited them from the original particle that had weak scale interactions. And there are no additional parameters, roughly. So every experimentalist is probably coughing up into their coffee knowing that that's not actually true. And it's true. When you look for supersymmetry colliders, all the other parameters matter. But actually, for the neutralino, for the dark matter candidate, for the most part, this is true. So this is actually pretty nice. I never said dark matter, and automatically I have a dark matter candidate. What else do we know? How else can we really check this really ought to be a dark matter? Well, one thing that the astronomers tell us is how much dark matter there is. Right? So how much dark matter is there? It turns out there is approximately 1 WIMP per coffee mug of dark matter in our galaxy. Right? Here I showed my work. I showed my dirty-ass coffee mug. It's about 1 GeV of dark matter per cubic centimeter. WIMPs are about 100 GeV. I have about 100 cubic centimeters of coffee in my coffee mug. And so this is fact. This is observation. The big question then is, my theory where I just waved my hand, said something about the Higgs, does this give me the correct amount of dark matter? Right? That should be the litmus test. How much dark matter does this theory predict? I gave you the mass. I gave you the interactions. Let's just calculate it. OK, here's how it goes. Here's a plot. And I've told all of the first years and second years, every time you show a plot, you tell what the x and y axes are. So the x-axis is time. As you go from left to right, this is moving forward in time. I'm writing it as a ratio of mass over temperature, dark matter mass over the temperature of the universe. On the y-axis is the number density. Those of you who took my GR or Simeon's GR course, this is the co-moving density. And this blue line is how much dark matter there is. So in the early universe, the universe is like some hot plasma soup, blah, 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 blah. Everything's in thermal equilibrium. Why? Because you have these electroweak interactions that come for free from the symmetry. What that means is from this hot group, you can produce dark matter. So ordinary stuff produces dark matter. Dark matter also annihilates into ordinary stuff, and that's in equilibrium. The universe cools down, and eventually around on the order of the mass of the dark matter, you no longer have enough thermal energy to produce pairs of dark matter particles. So that means this process stops. Ordinary matter stops producing dark matter, but dark matter still annihilates. And so if I look at this, I just say, oh, then dark matter just keeps annihilating. It stops being repopulated, and pew, I have no more dark matter. Well, that's a crappy theory. I'm missing something, though. What am I missing? Students, what am I missing from this story? Even my students. What am I missing from this story? Why is the universe cooling down?
Expanding.
Thank you. The universe is expanding. And as dark matter depletes itself, it's harder to find other dark matter particles. So in fact, while dark matter is annihilating and only annihilating, the universe is expanding and pulling it apart. And eventually what ends up happening is the interplay between the universe pulling dark matter apart and dark matter, when they find each other wanting to annihilate, ends up asymptoting to some freeze-out value. We call it freeze-out because you're no longer in thermal equilibrium. So you end up asymptoting. OK. Thus far, I have put in no numbers into my theory. I've just said there's a Higgs problem, rolled through this stuff. Oh, protons, some additional symmetry. I haven't put in any number into my theory. What would you say if I told you that this asymptotic value for how much dark matter there is just happened to be about 1 WIMP per coffee mug? This is like a magic trick. I've done nothing. I have not put any numbers into this theory. So that's almost true. In fact, it's within an order of magnitude. And for cosmology, that's pretty damn good. But this is actually so good that we called it the WIMP miracle. And really, when particle theorists see this the first time, they get religious. And I mean, they go to the church of the WIMP, right? And what are you comparing? You're comparing the rate at which the universe expands to the rate at which dark matter annihilates. So the rate at which dark matter expands to the rate at which dark matter annihilates. The relevant quantities are here. On the right, so those taking Yanu's field theory course, you can probably calculate this, or you will soon be able to calculate this. There are vertices that have numbers like G equals 0.6, the electroweak coupling. There are masses here that are around 100 GeV, the electroweak mass. And you get some number over here. On the left-hand side, those who took Simeon's cosmology course, all of the things you calculate here are M Planck. I don't know if you call them G Newton or whatever. It's M Planck. Right? This is the fundamental scale here is 100 GeV. The fundamental scale here is 10 to the 19 GeV. How is it that these two completely different calculations end up giving you something which is roughly what you actually observe for the WIMP? Right? That is really a miracle, or an incredibly cruel coincidence from some terrible universe that we're living in. And so this, for a long time, was the Bible for particle physics. Right? What is dark matter is some supersymmetric thing, and this review article from 1996 spelled out all the different ways to look for supersymmetric dark matter. Great. This is where the smugness came from. We were sure this had to be true. LHC would turn on, it would find the Higgs, we would find supersymmetry, the dark matter is the lightest supersymmetric particle, and we're done. Let's just find the Nobel Prizes in the 2000s, 2010s. So let's actually recap. The big problem, the only thing that particle physicists cared about in the 90s, again, this is a gross exaggeration, but let's say it that way. Why is the Higgs light? We had an elegant, beautiful, nice solution, supersymmetry. This symmetry means you have additional particles, right? It predicted more particles. Those particles tend to cause chaos. Anyone who's written down a theory of particle physics knows the more particles you put in, the more chaos you introduce. So the worst thing was that protons seemed to want to decay very quickly. So we had to fix that. We put a Band-Aid. Our Band-Aid tends to make some of these new particles stable. That automatically gives you dark matter. And without any additional futzing, the properties that these particles inherit from the electroweak sector, from the Higgs and its friends, give you dark matter with the actual abundance that we observe. So if we were back in the 90s and I was doing this, Ian's my first student, this is his thesis. And then Lexi comes along, and I'm thinking, oh shit, we have another thesis to write. Well, I was pretty sure this was a story. Okay, well, I know. There are other reasons why the Higgs might be light. Here's a good story. Extra dimensions. It turns out maybe the universe has extra dimensions. It turns out that this could be related to why the Higgs boson's light. Oh, that's interesting. Okay, a whole bunch of my colleagues have already worked out what this means, how that works. But I already saw the tea leaves, so I have a new symmetry. That gives me new particles, these Kaluza-Klein resonances. Okay. New particles, again, they always introduce chaos into your theory. So you end up brushing up against observations, these electroweak precision observables at this collider LEP, the precursor to the LHC. So there are observations that would not be valid if you just had these new particles running around wild. So we have to impose new order. So we make up a new symmetry, Kaluza-Klein parity. Okay. One of the byproducts of this new parity, in addition to solving this problem of these observables, is that some of these new particles are stable. Stable new particles. What's the rough mass of the stable particles? It's the electroweak scale. Why is it the electroweak scale? Because it was some symmetry partner of the Higgs, or the Higgs's friends. What is the interaction strength? Electroweak strength. Why? Because it's some symmetry partner of the electroweak particles. Now we're no longer religious. So is it surprising that you get the same abundance? No, they're the same damn numbers. They're just different names for the particles. Okay, cool. Whew, that was pretty good. Lexi's well along on her thesis, and then Adam shows up. So this is why it's always easier to be like the third or fourth student of an advisor. So Adam already knows how this game is played. I heard that there's a new way to make the Higgs light. Maybe the Higgs is a composite. It's made up of smaller subparticles. Oh, more particles, you say. OK, there's more particles. But if you introduce new particles to your theory, don't they mess up other precision observables? Indeed, they do. Let's make up a new parity to explain why these new particles can solve this problem while also not brushing up against this problem. These are typically called T parities. I bet nobody in this room knows what T stands for. It stands for TeV, and it's a completely crappy name. OK, so T parity. And now there's no surprise. You have a stable particle. Why? Because you have some new parity. What are the properties? It's roughly electroweak mass. It interacts roughly with electroweak couplings. Why? Because it inherited all of that from the electroweak sector. Because we were solving an electroweak problem. Why is the Higgs light? So the game is now pretty clear. New symmetry, something dangerous happens. It always happens. You come up with a new parity. Everything is OK. So this is the WIMP story. And it's like the fantastic love story of particle physics from the 1990s. And this is actually, these are two different photos, by the way. But my mom really likes this. It was in Science News for, well, never mind what it was about. But it's a love story of particle physicists had one big problem, the Higgs. And automatically, solutions to this problem gave us a solution to another problem. I mean, what else could you ask for? Well, you could ask for something. Thank you. You could ask for predictions, right? And actually, this is very relevant because I actually honestly think that the attitude in the 1990s was, we know what it is. We've got the LHC will just find everything. Let's just kick back. Let the experimentalists do whatever they want. No matter what happens, they will find this. What are the predictions? And it's particularly nice because I kept waving my hands about no free parameters, right? That's the magic of the WIMP. I had one problem. The solutions didn't actually give me that much wiggle room. And so we came up with this canon for how do you look for dark matter, right? And by virtue of the structure of the theory, dark matter talks to ordinary matter. So SM, standard model, is ordinary matter. Chi is dark matter. It talks to the ordinary matter in pairs. Why pairs? Because we made up this parity, right? You need to have pairs of dark matter talking to pairs of standard model. Why pairs of standard model? Because the standard model is complicated and there are lots of gauge couplings, gauge symmetries. So we know that dark matter can annihilate because we needed that to get the correct abundance. That annihilation happened in the early universe. Today, we can use gamma-ray telescopes or any other type of telescope to look at places where there's lots of dark matter, like the galactic center, and look for any remnants of ongoing dark matter annihilations. You can also look at colliders. So here, two ordinary particles, say protons, smashed together, typically produce lots of junk. Sometimes you might see lots of junk going in that direction and nothing going in that direction. And either conservation of momentum has been violated or there's invisible stuff going in this way. So that's another way to look for dark matter. And probably one of the best ways to look for dark matter is this thing called direct detection, where dark matter particles bump off of a nucleus of, say, xenon. By the way, for the students in the room, why xenon? Think about that. It's purely kinematic. Dark matter can bounce off of xenon, and you can detect what happens when you excite xenon molecules. It looks something like this. We have these gigantic 1-ton vats of xenon, and we look for some dark matter particle that goes through the crust of the Earth, hits this tub. It causes some kind of scintillation or ionization, and you can detect the electrons. And you just wait and you look for this. OK, so this is fantastic. We have a way to look for these. We do it. And you get these exclusion plots. OK. On the x-axis, it's really funny because these plots even call them WIMPs. They don't say dark matter. They call them WIMPs. The dark matter mass is on the x-axis. This is in GeV, so units of proton mass. So 30, 100, 1,000. So this is kind of where we're looking at for WIMPs. On the y-axis is the cross-section, so the interaction strength of the dark matter with nucleons. So this is in centimeters squared, which is kind of a funny unit for me. But actually, do people want to guess what the typical interaction strength of a weakly interacting particle would be? Weak, electroweak? So green is ruled out. All of these lines are different types of experiments, direct detection experiments. Green is ruled out. It's actually right around 10 to the 36. And if you play with the couplings, maybe 10 to the 39, 10 to the 40. But in this regime, right, the thing that I would have expected, if I just shake my theory and see what type of WIMP pops out, it would have been up here. And naively looking at this, man, that thing is dead. Now, of course, there's wiggle room. You can play with cancellations. You can tweak your theory even more. But now this isn't some elegant WIMP miracle. This is some Frankenstein theory. Meaning to say, this is what like all good romances, this is what happens. There is a breakup between the Higgs and dark matter. Something about this story where we start by solving deep problems about the Higgs has broken our hearts. And the breakup was here. If dark matter interacts with the standard model through the weak force, why the weak force? Because we had this electroweak problem with the Higgs mass. Then, sure, you get the correct relic abundance. Dark matter annihilates at just the right rate. That's the WIMP miracle. But every other process, which is just predict, once you know what this is, you predict the other ones. You see nothing. So where do we go from this? Well, I'm going with Team Flip. Maybe connecting dark matter to the Higgs was the wrong idea to begin with. So, OK, this now leads to the point a year and a half ago at the KITP. Is the WIMP dead? Here is my take on the WIMP being dead. Technically, it's not dead. Technically, it is not dead. If you told me that in 1 year, one of these direct detection experiments will discover the WIMP, it is a supersymmetric WIMP, and blah, 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 I'd say, oh, that's really cool. I wouldn't be like, oh, my God, my worldview has been blown. I mean, it would probably be an ugly theory, but maybe nature is ugly. Linguistically, it's not dead. And this is the problem, right? People will say weak for something which doesn't interact with a strong coupling. I mean weak as electroweak. So if electroweak is a coupling of 0.6, maybe you're thinking of coupling of 10 to the minus 6. Then okay, that's not ruled out. But that's a linguistic hook. Here's another politically important thing. Is it dead experimentally? Meaning to say, we built these amazing 1-ton detectors to look for dark matter. And even their plots say they're WIMP detectors. If I say, so I got in trouble on public radio for saying WIMPs are dead. And someone who works on one of these detectors said, do not ever say that in public again. And for good reason, right? If you sell your experiment as a WIMP detector, it's not good to have people like me saying WIMPs are dead. But the experimental program, these are dark matter detectors. And these are still the best, most robust ways to look for a broad class of dark matter theories. But emotionally, holy moly, my heart is broken. I am done with this thing. I am walking away. And I mean that in a technical sense, right? It's not that I have some deep connection to a particular SUSY theory. It's that this theory and the experimental process to discover this type of particle is so well developed that a non-tenured faculty member like me has very little to contribute to that path. Most theorists have very little to contribute to this path because this thing has been studied to death since the 1990s. So all we can say is, good luck to this program. Keep doing it because you might discover the WIMP, you might discover something else. But now it behooves the theorists to think about maybe it's not a WIMP. Maybe all these things are pointing to we should not be looking for a WIMP and we should generalize the way that we look for things. And Kurosawa said this best from Seven Samurai, I hate WIMPs. Okay, so that's the status for WIMP dark matter. The predictions just didn't pan out. So maybe the motivation is not the thing that we should wake up in the morning thinking about this story. So, lampposts. Where do we go now? I mean, by the way, this is both sad and exciting, right? If you are a dark matter theorist, this is exciting. This is where the opportunity is. You didn't want to be the grad student on the eve of the LHC knowing that you discovered the neutralino and blah, 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 because there's no more model building to be done. There's nothing else to understand. There's no fundamental theory to write. Now there's a puzzle. So the Higgs boson is still a problem. Maybe we'll make progress on it. But let's now think about dark matter on its own, or in context of these other smaller problems. Sorry, I shouldn't say smaller, other problems. And now the question is, well, all we have is that we know dark matter, we know the abundance. How do we connect it to actual predictions and experiments? Maybe we're too much in the Wild West. Maybe there are no rules. And actually, this is the thing that actually really annoys me. There's some kind of Dunning-Kruger kind of effect where people from outside the field, like outside of physics, will go on Twitter and say, well, of course dark matter doesn't interact with standard model. It's a completely different thing. You were so naive to believe that dark matter talks to standard model. And maybe that's true. But that story was a really damn good story. And in fact, there's still something to this, right? The pie, 25% dark matter, 5% ordinary matter. If dark matter had nothing to do with ordinary matter, why are these within an order of magnitude of each other? And people will say, oh, dark matter, maybe that's not a big puzzle. Maybe it's some weird initial condition, and God just started the universe with a bunch of dark matter particles. Really? Why don't we say, well, God just put the galaxies there, and we don't need galaxy formation? Why don't we say that God put the baryons there, and we don't need baryogenesis? Right? The universe is actually a very complicated and dynamical place. Right? You can't just say dark matter was there, and the universe inflated, all this weird stuff happened, and now the dark matter is here with this much abundance. And the fact that that abundance happens to be really close to the standard model is really compelling. So there are still some rules. Right? The elephant in the room, dark matter. How did it get here? Right? And again, when there is an elephant in the room, why is it still here? So the WIMP story was nice because it answered these questions. Right? Why is it still here? Because it was stable. Why is it stable? Because we had to do this step. We had to make up that parity. How did it get here? we had this really nice WIMP miracle, thermal freeze-out. The WIMPs were in thermal equilibrium, then it fell out of equilibrium, but the universe is expanding, so you had some leftover amount of WIMP. So maybe this is the roadmap. Maybe we start in the bottom right corner. We start with, we have dark matter. Let's try to cobble together theories that can help explain what it is. We have to answer how to get here. Why is it still here? Any theoretical framework will have particles and couplings. How do the answers to these questions inform these particles? How does this theory actually lead to predictions? Ideally, different predictions, new predictions, novel predictions compared to the WIMP. And then, afterwards, we can pontificate about whether this fits into our grand unified big picture theory that connects to the Higgs, connects to whatever. But that is a totally different step. Maybe we shouldn't have the hubris of answering all the questions in one fell swoop. So this is what it looks like on the ground. We have lofty questions and humble answers. What is a theory of dark matter? Okay, what do? We write down a bunch of wrong theories. I guarantee you, I will write down a whole bunch of wrong theories. But these are wrong theories that teach us something. Right? Let us see what we can learn about non-WIMP theories in terms of how did dark matter get here? Why is it still here? How do we use the mathematical structure of quantum field theory to interrelate different types of experimental searches? And then the other big question is, how do we frickin' discover it? And again, the humble answer is on a budget. Right? This is not the 1990s where we had a no-lose theorem. Build the Large Hadron Collider. I guarantee you, you will either get a Nobel Prize for the Higgs or 10 Nobel Prizes for whatever replaces the Higgs. So we have to use the tools that we have. And more, this is like some kind of, I don't know, like economic depression area, like creativity about using different types of observatories. All right, so let me just go run through some examples. So if not the WIMP, maybe dark matter talks to the standard model through some additional particle, a mediator, a new force particle. Right? If you want, you can just imagine every talk that Haibo has ever given in the past 10 years, this is the thing that makes itself interact. And that just changes the calculus about how these different types of experimental searches interplay, because the dark matter can talk to the mediator with any type of coupling strength. The mediator talks to the standard model with any type of coupling strength. And now it looks like I'm just completely generalizing the theory. So it's almost a silly thing to do. You get to keep the thing that you want. You take away the things you don't want just by adding more knobs to the theory. That's absolutely true. But then you get to be creative. So this is work with Adam. This is actually Adam's honors thesis. Once you have a new story, a new set of tools, you can tell new stories. Right? So here was a story where because of this new mediator, which interacted very weakly with the standard model, dark matter could hit the Earth, like the Earth becomes our detector. It loses kinetic energy and falls into the gravitational potential, falls to the center of the Earth. By virtue of these mediators, dark matter annihilation is enhanced, and you can annihilate into the mediators, which are very weakly interacting, and so they pass through the Earth, and they can decay into electrons, let's say, and we would predict a signal of upward-going electrons, pointing to the center of the Earth. Oh, that's cute. Why did you look for them? Oh, it just turns out that people who look for neutrinos, cosmic neutrinos, have a gigantic 1 kilometer cubed detector called IceCube looking for charged particles passing through the Earth. And they have really fantastic directionality. So this is a smoking gun signature for looking for dark matter through a neutrino detector. Oh, interesting. Then you could say, oh, this is kind of a cute picture. How else can we break this? So with Lexi and Ian and other collaborators, we've been looking at maybe dark matter interacts through something which is not quite a particle. So this is something which we're calling conformal mediators. It's basically putting the theory in extra dimensions through holography. And this really rewrites the rules for how you look for dark matter. All of these, you can still do these things, but the way in which this process is related to these other processes is completely changed because the extent to which you probe the extra dimension or the conformal wibbly-wobbly is now momentum dependent. Again, this is Kurosawa from Yojimbo. Maybe we should not be looking where there's light, meaning visible particles. Maybe we should be looking in the dark. So this is now, again, every talk that Haibo's ever given. But with Ian, we actually did something really neat, where rather than having dark matter, so Haibo's type of dark matter, self-interacting dark matter, you've heard the phrase. Rather than having self-interacting dark matter be a matter particle, maybe it's a force particle. So Ian and I came up with what I think is really the first really neat theory of self-interacting dark matter, where the dark matter is a force particle. This is what the theory looks like, but it's a lot more elegant than it looks. Maybe we need to look for other detectors. So this is work with Aniket, a postdoc in our group. And one thing that we thought about was, well, neutron stars are these really exotic, clean environments. Every neutron star looks like every other neutron star. And they have these huge gravitational potentials, which like to suck in particles gravitationally. And we know dark matter interacts gravitationally, so maybe dark matter will crash into a neutron star and impart heat onto the neutron star. And this constant flux of dark matter hitting neutron stars will heat up the neutron star. And with telescopes like James Webb, if we discover some nearby old neutron stars, we can actually detect the temperature of these neutron stars and determine that there's dark matter kinetic heating. Well, the really neat thing, by the way, that Aniket did, and I think right now Aniket's the only person in the world who can do this, is the original idea of hitting neutrons. This is a fixed target experiment in the parlance of particle physics. You have a stationary neutron, and dark matter hits it. What's way more interesting is dark matter hitting the electrons, because now you have a particle collider where the electrons are actually relativistic because they have a Fermi surface. So this is relativistic collisions of dark matter. Another really cool thing that we've been thinking about is maybe we're looking at dark matter at the wrong time. Thinking about pristine environments. One of the really pristine environments for looking for dark matter happens to be early stars, early galaxies. Right? Looking at current galaxies is really mucky because you have things like supernovae injecting energy. But in early galaxies, the only things that would be annihilating and injecting energy into the early galaxy could be dark matter. Where does this energy go? So this is something that Katie Mack had been thinking about for WIMPs for a long time. And at this conference, at KITP, we actually met up and started thinking about, well, how do we generalize that? And it turns out the types of handles that you get from playing with different types of dark matter models can actually give you a handle to play with star formation. OK, so what? Dark matter injects energy into an early protohalo. That energy can affect the star chemistry, or the gas chemistry. In particular, you can dissociate H2, molecular hydrogen. H2, for all of the astronomy people you all know, is really important for star formation. Right? It's a coolant. And if you dissociate the coolant, you're changing the star formation rate. And this can lead to all sorts of interesting predictions. One thing which is really curious is that this could seed supermassive primordial black holes. Right? These black holes where there are these quasars which have black holes in them. They're about 700 million years old. And we have no idea why they're there because there weren't enough population 3 stars to actually form black holes at that time. Maybe what's happening is dark matter is cooling down these, dissociating the coolants and allowing these population 3 stars to form and produce these supermassive black holes. And these black holes are the footprint, the fingerprint of dark matter in the early universe. OK, so once again, how are we moving forward? With lofty questions and humble answers. Right? What is a theory? We don't know. Let's write down a whole bunch of wrong theories where each one may have a grain of truth or something to learn from it. How do we discover it? Now we get to be creative. All right, thank you very much. I was informed that there is no budget for the Colloquium speaker to go to dinner. Any questions? No questions? Good. Oh, I've got class in 30 minutes.
So, why are we so religious about the standard model? Could it be that,
Good.
that we have some other theory that explains the standard model and the dark
Good.
matter at the same time?
Good. So the question is, why are we religious about the standard model? The answer is that we've discovered the standard model, and the standard model, is the unique renormalizable theory that describes everything that we have. Does anyone working in particle physics religiously believe that standard model is it? No, absolutely not.
I'm saying something else, like maybe just you think of something else that leads to the standard model, but also as a side effect that.
Oh, that would be great. Yeah, that would be great. So the standard model is here. Maybe there's some theory here that gives you a standard model and also gives you dark matter. So that would be great. And you can cook up any number of theories, exotic, elegant theories that give you standard model and dark matter. That's different from discovering the theory. So the point of view now is, I don't need the elegant unified thing. I need, what are the handles that this thing predicts? Maybe this predicts 5 new particles that are all electroweak scale, or 5 particles that are EV scale. I should look for those. So now I will classify my search in terms of theories that require 5 particles that are like this, or theories that require new particles with electric charge, or theories that have an axion, or theories that, so the thing that we care about the most is, how do we discover it? And that's how we want to classify the theories. Rich.
So, is it really, so since supersymmetry is it sort of really over, and you talk about ice cubes,
Yeah.
but you haven't mentioned colliders. Are things really over for the colliders?
Oh, absolutely not. Good. So the question is collider physics done? And Rich is asking me this with Bob staring me right in the face. So gun to my head. Absolutely not. And it's in the same way that direct detection is not done, right? Absolutely not. For one, the question of the Higgs is still a huge question. We may discover, Bob may discover supersymmetry, again, in 2 or 3 years. Is that 1 year? So Bob's promising 1 year. In 1 year, we'll discover supersymmetry. And what will that mean? It just means that the theory was not quite as elegant as we had predicted before. And if that were the case, we will all be celebrating in the streets. But it means, it also means that maybe we keep saying this year after year. If that direction doesn't require any more creativity from the theorists, maybe we should be thinking about broader possibilities.
So the question is, more broader possibilities.
Yeah.
Does it make predictions?
Oh, absolutely, absolutely. So the thing that Lexi's working on right now are really exotic collider signatures for these conformal wibbly-wobbly theories. Yes.
So is the argument that the dark matter interacts with the standard model particles, not just gravitation but something else? One, gives us something to do, but also the fact that the abundance matches the
Yeah.
mirror.
Yeah.
Is that the only reason to believe it interacts other than gravity? Or would
Yes,
it be,
good.
Would it be completely
Good.
fine with having a completely sectoral
Good.
masses, which are just gravitational and that's it?
Excellent, excellent. So Vivek's question is, really, how much do you really need the standard model and the dark sector to actually talk to each other? Perfect. And I think that the idea that the dark matter abundance could be tied to the standard model is very compelling. But you're right, that is an aesthetic point. That is my religious view of the year. It need not be. But from a field theory point of view, if you have a completely disconnected sector, just from the point of view of what types of portals there could be, there is some minimal coupling that you expect to show up.
Yeah, gravity. That's not good enough.
Even gravity. And there are people who say, maybe you have a dark electromagnetism and a visible electromagnetism, and maybe these two things interact. Maybe they interact only through gravitational interactions. It's a six loop process to get this to happen. And they still, the precision with which we are looking for these things, they are still things that are predictive in current experiments for some regimes. So you're right. You could have a completely disconnected dark sector. And that's where HIBO self-interacting dark matter becomes a really interesting thing, because now that becomes the main way to look for dark matter. But it is actually much harder than you would naively think to completely sequester 2 particle physics pieces. Yes?
Maybe a related question, because you cannot fit gravity into the standard model yet. Is it
Yes.
too much to ask him something with the standard model, something that's similar to that?
Good.
To be able to explain something that's basically a problem in gravity?
Good. So, so that was the first slide of we agree that dark matter is a particle. So the question is, maybe this is some deep gravitational problem, and quantum gravity maybe will solve this, and why are we doing this? The quantum gravity scale is a Planck scale. The dark matter scale seems to be much lower. I mean, there's a huge swath of possible scales for dark matter. So naively, I have no reason to believe that dark matter has to do with quantum gravity. Like, why should we be looking at things on galactic scales where you have this weird, what looks like a particle, talks like a particle, really ought to be a particle, but it's actually coming from quantum gravity, which is not operative at these scales. Like Newtonian physics should be valid there. It could be. I mean, people write these theories. None of them make sense to me. You may ask a different question.
Which is to do with you said that the hierarchy problem was connected, now it's disconnected, but that hierarchy problem still needs a solution.
The hierarchy problem still needs a solution.
So
And I will.
Okay, so if that needs a solution, meaning you need something standard model plus something else.
Right.
So we have one unknown over there.
Right.
And then here's another unknown.
Right.
And you're trying to come up with a theory which fixes one.
Yeah.
And you're assuming, is there some sense in fixing one?
Yeah. Oh, absolutely. Good. So Vivek's asking, you have two problems, and the story that I told was the standard model problem informed the dark matter problem. Now I want to think about dark matter. Maybe the dark matter problem informs the standard model problem. Yeah. You want to make dark matter WIMPs again. Yeah. No. And this is actually this is a interesting and fun question. But yeah, it's not. Let me end with this bit of propaganda. The dark matter problem is an actual problem because we know dark matter exists. If it weren't a particle, if it weren't, that's a much bigger revolution. So the conservative thing is dark matter exists. It's a particle. We should figure out what it is. The hierarchy problem, I think, is a deep problem, but it's also, in some sense, an aesthetic theorist problem.
So you're saying the standard model is fine without fixing it? It is what it is.
The standard model is tuned. So it's this ice cube in the oven problem. But yeah, look, maybe that's the way the oven works. Maybe we're just incredibly lucky. Yeah. It makes me sick to my stomach, but it could be true. Okay, so let us thank the speaker enthusiastically one more time.